So, welcome everyone to this week's Origins Colloquium. It's a great pleasure to welcome Kevin Heng to give the talk this week. So, Kevin received his PhD from University of Colorado in Boulder. It was 2007, I see here, right? And then had postdoc positions at Princeton, the Institute for Advanced Study, as well as ETH Zurich as his Wiki Fellow, before moving to University of Bern, first as an assistant professor, and then director of the Center for Space and Habitability. Since 2022, he has been chair professor of theoretical astrophysics of exosolar planets at LMU, Ludwig Maximilian University in Munich. And just now, and maybe we'll hear about it, he is setting up a new center on geoastronomy. So he's received a number of awards, including prestigious grants from the ERC, Consolidator, and most recently a Synergy grant. So welcome, Kevin. We look forward to your talk and discussion.
Thank you for the invitation and very kind introduction, Jonathan. So I will try to make this 30 minutes as interesting as possible for you. I want to tell you the philosophy behind this because roughly maybe 4 years ago now, when I was still director at the Center for Space and Habitability, I slowly came to the realization that many others have before me, that if I really wanted to understand rocky exoplanets, I could no longer just be a physicist, that I actually had to talk to geoscientists and understand their language, understand the questions they're asking, and transform like maybe part of myself into a geoscientist. So at that time, the center had a CSH fellow that I hired, called Meng Tian, whose name is on this slide, who eventually followed me to Munich. And Meng is a computational geochemist trained at Yale and Oxford. And he was the one who introduced me to this kind of thinking. And after several attempts, we got this ERC grant where I will talk briefly about it, where I am actually the minority partner on this grant. So I'm the only astrophysicist. And Steve is actually a planetary geochemist, and Fabrice is a well-known experimental petrologist. So Fabrice does, among other things, simulations of magmas in the laboratory, trying to understand laws and so on. I really would like to expand my intellectual horizons, and you can see the goal of what we're trying to do. We are trying to merge in a very deep way the principles of geoscience and astrophysics. We're not just interested in what we are actually trying to understand what are the principles in geoscience that can transfer over easily and allow us to understand exoplanets. But I'm also interested in questions that we may never answer, like how do I generalize the carbon cycle for rocky exoplanets in general? No idea. We tried, but I don't think it's possible. How do you compute the topology of a rocky exoplanet? I don't think that's possible either. But if you ask the question, how do I compute outgassing on other planets? I think that's possible. I think that problem can be generalized, and that's what I will talk about today. So I want to start with asking questions like, what are the solar system planets made of? Because I think it's quite instructive. So if you look at the terrestrial planets in the solar system, um, you will notice that they have rather different densities between 4 to 5-ish grams per cc. And those bulk densities actually tell you very little about their atmospheric chemistry. Mars, for example, Mars and Venus both have carbon dioxide dominated atmospheres with some nitrogen, but the surface pressures are different by roughly a factor of well, Mars is 1 millibar and Venus is close to 100 bar, so that's several orders of magnitude. And Earth has nitrogen and oxygen and CO2. And you will notice that this is very different from our sun, implying that it's actually not so straightforward just looking at the atmospheric chemistries of terrestrial planets to figure out how they form. You need much more information than that. And this is because of the interactions between um, geochemistry and physics, essentially. So the Earth, this is one of my favorite papers on this topic by one of my co-PIs of the grant, so Fabrice Gaillard. If you have never read it, I really recommend you read it. It's beautifully written. And this figure is trying to show you that even for the Earth, the history is very complicated. So the Earth probably started out with some kind of hydrogen helium dominated nebula inherited from the protostellar nebula, the beginnings of the sun. Um, then at some point it had a reduced atmosphere, mostly made of hydrogen and CO, with an underlying magma ocean. This magma ocean at some point solidified, and volcanic outgassing became important. And as the hydrogen escaped the atmosphere and biology oxidized the atmosphere, this eventually produced the modern atmosphere that we see, where CO2 is supplied on long time scales by volcanoes. So for the Earth alone, it's worth keeping in mind that these processes are so complicated that it's really difficult to go from a protostellar disk or protoplanetary disk with helium, hydrogen and helium and dust, and evolve that all the way to a mature rocky planet with uh, differentiated core and mantle. That's really difficult. But one thing that this paper points out, which I wanted to bring to your attention in case you haven't thought about it, is that you can actually understand outgas atmospheric chemistry. I'm sorry, there's one thing I did not really explain very well, which is that as the Earth form and evolve, um, there's the process of ingassing where the nebula gas and whatever gas is produced is being essentially shoved into the magma. And that's because one of the effects that we physicists don't think about is that gases are actually very soluble in magma. Like gases like water are very soluble. And at some point, this is gonna outgas through volcanoes and other types of outgassing. And and this paper points out that one of the parameters that controls outgassing is actually the pressure, which is interpreted as the surface pressure in this paper. So, in other words, um, terrestrial planets with different masses of atmospheres, which have different surface pressures, would express themselves differently chemically. So here's a model. This is a very simple toy model. It doesn't explain the whole picture, but it makes the point that if you just assume a magma with the composition of basaltic rock, which is found on Earth, and and you give it some temperature, about 1600 Kelvin, and all you change is the pressure in which you exert on this magma, which is directly related to the atmospheric pressure. You can actually produce mixtures of gases that are consistent with what you see in the terrestrial planets. So Io, for example, which has a very thin atmosphere, would produce sulfur dioxide and water. Mars would produce also sulfur dioxide and water, but more water than sulfur dioxide. Earth would produce a combination of water and carbon dioxide, and Venus would produce dry carbon dioxide. And then, so this zero order explanation seems to work for the outgas atmospheric chemistry of the solar system. So the next question I just wanted to make it a point, and I'll come back to it later. The next question is, what are exoplanets actually made of? I had a whole section on this, which I cannot give you, so I'll give you a condensed version, which is most of you are probably familiar with this figure, which is the radius valley. So if you go out and you measure the sizes and orbital periods of transiting exoplanets, and you do a statistical analysis, you get this double peak distribution in size and period. And if you sum this up over orbital period, you get this famous distribution at two peaks, one at roughly 1.3. We have given names to these features. So the gap in between the two peaks used to be called the Fulton gap after the first paper, Fulton et al. In 2017 that discovered this. Nowadays, we call it the radius valley. There's also this radius cliff at 3 Earth radii that I will not talk about. But what is interesting, there are two features that are interesting about this. So you see that, roughly speaking, the radius associated with the first peak is roughly twice that of the radius associated with the, I'm sorry, the radius associated with the second peak is roughly twice that associated with the first peak. And now if you pretend that the planets associated with these peaks have roughly the same mass, which they do not, you can estimate what the ratio of bulk densities would be, and that will be a factor of 6. And so this implies that if the second peak is associated with mostly gaseous things, say 1-ish grams per cc, then the second peak must have Earth-like bulk densities. It must be rocky. So just from order of magnitude, you can understand that. And one of the points I like to make when I give different versions of these talks is that you can do the following analogy. So in the solar system, you have the terrestrial planets which have secondary outgas atmospheres. Then you have the ice and gas giants which have so-called primary atmospheres, where to zeroth order, the atmospheres look like the sun. Not really in the detail, but zero to zeroth order they do, which means that the primary atmospheres actually contain a memory of how they form from the primordial nebula. So by analogy, if you have objects in between the terrestrial planets and the ice and gas giants, they must have some kind of hybrid atmosphere, meaning that they neither have atmospheres that are completely controlled by outgassing nor by planet formation, but something in between. So here's a cartoon that just emphasizes this. So the first channel is you start out with some kind of rocky core with a hydrogen envelope. The planet is not massive enough to hang on to the hydrogen envelope, so it loses that to zeroth order. Then geochemical outgassing takes over and populates the atmosphere and this is called a secondary atmosphere. It is possible that in nature you have rocky cores that are just so happen to be massive enough for whatever reason, so that they hang on to some amount of hydrogen and helium. And the outgassing then happens into this hydrogen and helium. And so it will produce a fundamentally different chemistry. And I think it's reasonable to ask what this chemistry actually is. What would this actually look like? And this is actually the focus of what I will talk about later. And this kind of thinking is motivated by data that's starting to come out. My favorite object is actually not K218b. It's actually this object. It's TOI 270d. I think it's a remarkable object. So it's a sub-Neptune in that, so meaning it belongs to the second peak, not the first peak in that bimodal distribution. It's a system. It's an M3 star with one super Earth and two sub-Neptunes. And one of these sub-Neptunes has a very interesting set of properties. So it has a radius of roughly 2 Earth radii, a mass of roughly 5 Earth masses, and a density in between that of Earth and Jupiter. So it's neither pure rock nor mostly gas. It's 2.7 grams per cc. Now, if you trust these authors, let's just trust these authors for a moment that they have done a good job of taking the spectrum, doing atmospheric retrieval, and inverting the spectrum for chemical abundances. Then you get a very striking set of chemical abundances, which is that methane is roughly 2% by number, and carbon dioxide is also roughly 2% by number, which is interesting to me because this means that in a hydrogen-dominated atmosphere, you have a very reduced molecule that's comparable in abundance to a very oxidized molecule. That's interesting. And that exists alongside 8% water, which is quite a lot. And now if you convert these molecular abundances into a mean molecular weight, you get a mean molecular weight of like 5.5 plus minus 1, roughly. And this is again interesting because the mean molecular weight of Jupiter is roughly 2.2. So that's dominated by hydrogen and helium. The mean molecular weight of Earth is 29. It's dominated by hydrogen. And this thing is neither, is something in between. So at this point, you could ask the question, which many people are asking, are sub-Neptunes actually smaller versions of gas giants, or are they larger versions of Earth? And by the end of this talk, I think I will convince you that they are neither. Sub-Neptunes are actually their own unique thing. And they have a set of conditions where they're not analogous to either being smaller gas giants or larger terrestrial planets. So the next question I want to ask is, what are the birth properties of this bimodal distribution of small exoplanets? The other way of asking this question is the bimodal population of mature because these are transiting exoplanets, it's a observational bias to some extent, consistent with a single underlying seed population. And if you read the papers of James Owen and company, the answer is yes. So you can explain this bimodal distribution with one underlying seed population. And I don't have time to actually give you the detailed explanation, but the hand wavy explanation is that if you start out with some initial population and you subject it to atmospheric escape, then the super Earths are roughly the strip rocky cores of this population. And the sub-Neptunes are the one that are massive enough to have hung on to their atmospheres, such that the atmosphere of the sub-Neptune and its rocky core have comparable influence on each other and therefore comparable volumes. And this picture is consistent with the fact that the the first peak, the second peak has a radius that's roughly twice that of the first peak. And if you want to talk about this more, I have a slide from one of James Owens' paper later. So I have given versions of this to students, the full version. So I thought it's instructive to ask these simple questions like, what is the atmospheric mass of a sub-Neptune? I think this is very instructive. I found it very useful. So in other words, I have just made the claim, according to reading James's paper and others, that a sub-Neptune is an object that where the volume of the core and the volume of the atmosphere are comparable. And therefore, the radial extent of the core and the radial extent of the atmosphere are roughly the same. But what is the mass fraction? What is the mass of the atmosphere to the mass of the core? What is this value for H2 dominated atmospheres? And what is this value for water dominated atmospheres? And since we have very little time, I will not wait a few minutes for you to guess, but you can think about it in your head. And actually, the number is interesting. So for H2 dominated atmospheres, you need just 1% of the mass of the core in hydrogen to make an atmosphere that has the same volume as the core. And this is where sub-Neptunes are very different from gas giants. So sub-Neptunes are not scaled down versions of gas giants because even though the atmosphere has a lot of volume, the mass is controlled by the core. And if the mass is controlled by the core, this means that if the core is outgassing, this would overwhelm whatever is in the envelope. If you ask the same question for water-dominated atmospheres, you would need roughly 50% the mass of the core in water vapor and other phases of water to make an atmosphere of the same volume. So I'm not a planet formation theorist. You can think about how likely that is. The second question is, what is the surface pressure of a sub-Neptune? And what equation do I actually use to estimate the surface pressure given the atmospheric mass? And it's actually Newton's second law, because Newton's second law is F equals to ma. The pressure is the force per unit area. So the force is the mass of the atmosphere multiplied by the acceleration due to gravity. And if you divide this by the surface area of the core, this would give you an order of magnitude estimate for the surface pressure of a sub-Neptune. Now, if you pretend it's an Earth mass core, and you give the atmosphere 1% of an Earth mass, this would translate to a surface pressure of roughly 10 kilobars. So in geoscientists, some geoscientists would like to use the unit gigapascal. And this is, again, an interesting number because gigapascal is high enough that you have to worry about mixed phases of matter, which I don't in this talk. But it's not quite high enough that you have to worry about metallic hydrogen for Jupiter. So you would need roughly 100 GPa to worry about hydrogen turning metallic. And this is yet another reason that Sub-Neptunes are not quite scaled down versions of Jupiter, at least in the detailed physics. The third question is, what is the surface temperature of a sub-Neptune? This is much harder to estimate because you need to have a planet formation model. You need to assign some kind of remnant heat of formation. You need to do radiative transfers to account for the cooling of the object over time. And papers like this paper have done this kind of work, and they have determined that the temperature is roughly 5,000 Kelvin. So, so that is interesting because um, 5,000 Kelvin is, first of all, above the melting point of rock, both the liquidus and the solidus. So these rocky cores are molten, at least at the surface. But the temperature is also interesting because the temperature of the magma on Earth that gives rise to volcanic outgassing is roughly 1600 Kelvin. So the temperatures are quite different. And it also presents challenges because a lot of the thermodynamical quantities we need to calculate outgassing are motivated by Earth. And we actually do not have these experimentally measured quantities for sub-Neptune temperatures. So this is something we need to work on. So there's this, finally, I come to this wonderful paper by Rogers and Owen in 21, where here's the following idea. So they match not just the observed radius distribution, but they match both the radius distribution and the orbital period distribution. And they construct a time-dependent model that accounts for atmospheric EUV and X-ray driven atmospheric escape. And through iterating this with the observed distribution, they try to match the observed radius value for a single underlying seed exoplanet population. And the results are striking. So the results are if you if you try and match this, so don't worry about what is model 2 or model 3. But if you try and match the observed radius distribution in gray, which is the first panel on the left, then the answer is that you get a distribution of core masses, which peaks at 4 Earth masses, and a distribution of atmospheric mass fractions, meaning the mass of the atmosphere divided by the mass of the core, of roughly 2%, which matches the roughly 1% intuition I just told you about. So this probably doesn't generalize to all of the universe, but at least in the nearby universe, for which we can measure a precise radii, and the the small planet, the small exoplanet population is described by a distribution of core masses peaking at 4 Earth masses and having mass fractions that are roughly a couple of percent. The next question after you understand this is, what is the variation in atmospheric chemistry across this radius valley? This is my interest because the idea is that if you could understand the atmospheres of these sub-Neptunes, then you could go out, you can use web data, you could constrain things like the mean molecular weight, and you can confront your models with this data and see if you learn something new. So to do this calculation, I assume that sub-Neptunes have so-called hybrid atmospheres, consistent with what I told you about, meaning that they have cores and atmospheres of comparable volume, where the atmospheres are made of hydrogen and helium mostly, but the mass is dominated by the core. And I want to calculate outgassing into this hydrogen helium dominated atmosphere and see how this looks like. So I do not have enough time to give you all of the details, but you can ask me questions. I want to give you some intuition. So this is a summary of what I told you about, the order of magnitude summary. So the core is roughly a few Earth masses. The surface pressure made up due to mostly hydrogen is roughly 10,000 bars. The surface temperature is roughly 1,000 Kelvin. The radius of the core and the radial extent of the atmosphere are comparable. To calculate outgassing, I need to know the TP conditions at the surface of the core, but these parameters must be related. For example, the mass of the atmosphere must be related to the mass of the core, and it must be related to the equilibrium temperature, which is the proxy for how much flux this sub-Neptune is receiving from the star. Another way of saying this is that more massive cores that are further away from the star would, on average, retain more atmospheric mass, you think, naively. So these three numbers must be related. Now, if the envelope is more massive, that means that the surface pressure is higher, which means that the planet would probably retain more heat, which means that the surface temperature of the core must be higher. So T and P must be related. And if you allow the planet to cool longer, meaning it has an older age, then the temperature would also drop. So these three numbers must also be related. So in other words, what I'm trying to tell you is that is doing an outgassing calculation by itself is not terribly interesting. You want to do an outgassing calculation that is tied to and evolution Rogers and Owen would like to combine temperature pressure conditions computed by Rogers and Owen with an outgassing model to figure out what the atmospheric chemistry looks like. So I'm actually very excited about this plot, and I'll try to convey my excitement. This information is in principle present in the calculations of Rogers and Owen, but they were never presented because they were not relevant in the context of that paper. But hidden in those set of calculations are the temperature and pressure conditions at the surfaces of these molten rocky cores. And so what I've shown you is the temperature and the pressure, and in color I have shaded the core mass. And you can see that it fits your intuition, meaning that cores that are more massive, that have the brighter colors, would have higher pressures, meaning more massive atmospheres, which retain more heat and therefore have higher temperatures. So you see it's related. So I would like to take all of these different instances, these TP conditions, and I would like to tie that together with an outgassing model to figure out what the hybrid atmosphere looks like. So let me sketch to you what this looks like. So one would take the data-driven radius valley constraints, the TP conditions. You would merge that with a set of parameters that I will describe. You would feed that into an outgassing model. You would worry about things that usually geoscientists worry about rather than physicists, meaning that you worry about the fact that hydrogen and water are actually dissolved in magma. So you have to put in solubility laws. You actually have to worry about the fact that at these conditions, you cannot assume an ideal gas. And so there are these corrections called fugacity coefficients, which I will describe. So you have to put that in the model. And what you get out are molecular abundances of a bunch of molecules, water, CO, CO2, methane, hydrogen sulfide, and so on. And from that, you can calculate the mean molecular weight, which is what I'm after. How am I doing on time? 31. So I'm going to finish soon.
Yeah, you're good.
So, yeah, I don't know how interesting this is. If you stare at it, you basically have 8 equations and 8 unknowns, so 6 chemical reactions. So I guess the thing to say is that you can mathematically you can formulate the equations versus the unknowns in an arbitrary number of ways. And I've chosen this way because I think it makes sense to me physically rather than mathematically, which is that there are 6 chemical reactions and 5 so-called equilibrium constants. And I chose my key parameters as the carbon to hydrogen ratio of the envelope, so the so-called metallicity that we like to call it in astronomy. And I've chosen another parameter to be the silicon to oxygen ratio, which is a proxy for the composition of the magma. And I don't want to talk about numerics, it's not so interesting. So 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 why do I choose these parameters? So I haven't explained to you what a fugacity is, so I will explain it to you later. But I've chosen parameters to be the oxygen and sulfur fugacities. And in particular, the oxygen fugacity describes how oxidized the rocky mantle of a sub-Neptune is. The other parameter is the carbon to hydrogen ratio, otherwise known as the elemental abundance of carbon. Some astronomers call this the metallicity. And this describes the lowest order, the enrichment of the hydrogen envelope. Then the other parameter is the silicon to oxygen ratio, which describes, again, the lowest order, the melt composition. And then there's the mass of the melt, which is not so interesting for our discussions. Now, I would like to tell you about fugacities first. This is something that I struggle how much I should talk about. So the fugacity is the generalization of the partial pressure for non-ideal gases. Surprisingly, this is actually not derivable from first principles. I was quite surprised when I realized this. So if you go back to your thermodynamics, you can write down a general equation for the Gibbs free energy. And this is the first equality that you see. So G, the Gibbs free energy is valued at some reference pressure plus this integral that involves the mass density. Now, if you assume an ideal gas, you can evaluate this integral, and that's the second equality. So this is only for an ideal gas. For a non-ideal gas in general, you cannot evaluate this integral. But what the sleight of hand, the trick that geoscientists have done is that they take the equation for the ideal gas outcome and they say, let's let pressure go to something called the fugacity, where the fugacity is the pressure with some order of magnitude, or maybe it's not always order of magnitude, with some dimensionless correction factor that we call the fugacity coefficient. So this is mathematically not consistent because you can't take the expression for the Gibbs free energy for ideal gases and then just make this kind of substitution. But this is very ingrained in the geoscience literature. We can't change it. So using this formulation, there's a very long and rich literature on measuring this fugacity coefficient. So let me show you what these are. So these are the fugacity coefficients measured from experiments as a function of pressure. And I have shown you a range of temperatures ranging from Earth-like magmas to Sub-Neptune-like magmas temperatures. And the thing to take away is that the fugacity coefficient is roughly 1 at pressures of 1,000 bars and below. So in other words, for 1,000 bars and below, you can get away with ideal gases. But if you remember, the order of magnitude surface pressure of a sub-Neptune is 10,000 bars. So once you go to 10,000 bars, these fugacity coefficients are significantly different from unity, which implies that you cannot assume ideal gases when you model outgassing at sub-Neptune conditions. So this is an important point. The other thing to explain to you is something called the oxygen fugacity. So the oxygen fugacity would be the generalization of the partial pressure of oxygen if it existed in a gaseous form. And the amount of oxygen that exists is usually buffered by a reaction such as this. So the iron reacts with oxygen to give you iron oxide. And you can imagine that the partial pressure or the fugacity of oxygen in this reaction depends on the temperature of the melt. And typically you would think of some reaction like the iron-Woodstack reaction, which is this reaction in blue, to figure out what the oxygen fugacity is. In other words, if you knew how much iron there is and knew how much iron oxide there is, you could figure out O2. This is what we do for Earth. But this reaction is not particularly relevant at temperatures that are much, much higher than that of Earth's magma. So one question I have, which I have no answer to, is what buffer or chemical reaction should I be thinking of at 5,000 Kelvin? Is not actually clear to me. And the other thing we can talk about is how do you actually choose an absolute value of FO2 under sub-Neptune conditions? We can talk about that later if you like. I would like to show you the outcome and I would like to stop. So here's the outcome. Let's not talk about the dash and the dotted curve. So the vertical axis shows you the mixing ratio of the atmosphere, so the relative abundance of gases by volume as a function of temperature, and I've assumed sub-Neptune-like surface pressure. And the striking feature that you see is that if you concentrate on 5,000 Kelvin, the atmosphere looks very gas giant-like. It's mostly hydrogen in this case, with some methane, some water, and some other species, right? But it's mostly hydrogen. It's a hydrogen-dominated atmosphere at 5,000 Kelvin. But as you go from 5,000 Kelvin to 2,000 Kelvin, so within the space of 3,000 Kelvin, you can see that all of these abundances start rising just because of Gibbs free energies, such that when you reach 2,000 Kelvin, it's not the mean molecular weight of this atmosphere is not exactly hydrogen dominated. So this is the mean molecular weight. So at 5,000 is 2-ish. It's consistent with what Jupiter has. But again, there's this thermodynamic effect that as you go from 5,000 to 2,000, there's a steep increase in the mean molecular weight to even roughly like 20 in this case, because the atmosphere gets less and less hydrogen dominated as the melt temperature decreases. This is interesting because as you go from more massive sub-Neptunes to less massive sub-Neptunes, you expect just from thermodynamical principles that their atmospheres should get less and less hydrogen dominated because of this property. So finally, to answer this question, how does the mean molecular weight vary across the radius valley? If you understood what I told you, you can actually guess the answer. So if you go back to this plot, let's start going from large planets to small planets. So if you go as you go to smaller and smaller planet sizes, the all things being equal, the core is less massive, so you retain less atmosphere. And if you retain less atmosphere, then the surface pressure is less, which means that you retain less heat over time, which means that your temperature is lower. And now the thermodynamics would then imply that as you get to smaller and smaller planet sizes, the atmosphere will become less hydrogen dominated. The mean molecular weight will increase. If you go along the horizontal axis, as you go from long orbital periods to short orbital periods, the the planet receives more and more flux from the star. This means that it's more and more difficult to hang on to the atmosphere, which means that the atmosphere is less massive, which means the surface pressure is lower, which means it retains less heat, which means the temperature is less, which again means that the mean molecular weight increases. So if the mean molecular weight is increasing in both directions, this suggests that it will increase in the diagonal direction as well. And what I cannot tell you is the angle of this arrow in white. To know that angle, you have to actually do the calculation to see which is the dominant effect. So here's the calculation. So for each of these, um, if you remember, I've showed you a plot where I have the temperature pressure conditions for a whole population of sub-Neptunes. And what is important to tell you is that this population of sub-Neptunes is actually constructed to match the observed population. So I take that data-driven population, and for each sub-Neptune, I calculate what the mean molecular weight is. And you can see, as I described to you in a hand-wavy fashion, that as you go towards the radius valley, you have this natural increase in the mean molecular weight due to the principles I just described to you. So that's the prediction. The prediction, and I've tried many different combinations of the parameters, and this gradient is pretty robust. Should I stop, Jonathan? I think I would like some time for
Well,
discussion.
maybe if you can wrap up in a minute or so with a conclusion, then we can discuss more. Yeah.
Here's the conclusion. So the gradient of mean molecular weight robustly exists across the radius valley, and this is driven by the TP conditions and the thermodynamics, which is what I told you. Now, the strength of this gradient is controlled by the how oxidized the mantles are, and actually not by the metallicity of the atmosphere. We can talk about this. This is also a surprising result.
Hmm. Great. Thank you very much for a fantastic talk.
Thank you for your patience.
So we have time for questions and discussion. So please raise your hand in the Zoom. Joe and Ryan, please help me in Sweden and in Virginia. Maybe I can start with, one of the other conclusions of Rogers and Owen was that core composition was very volatile poor and quite uniform and iron rich. Let me see here. So are you saying that that you can explain the radius valley just from outgassing and you don't need accrete any primordial atmosphere?
No, I'm not saying that at all. I'm saying that if
Because
I
on some regime, you're outgassing a lot of hydrogen. maybe I missed that point then.
Um, no, I'm not saying that at all. I'm saying that I'm saying that Rogers and Owen does the first. You can't. I don't think you can see my cursor,
No, I
but
can. Yeah, we can.
you can. So the first arrow going from the primordial atmosphere to this object is essentially given by the calculations of Rogers and Owen.
Okay. Right.
And I am trying to do the second arrow.
hmm So let me then see, because well, you showed some models where I thought the outgassed atmosphere was also hydrogen rich in the end, but is that because H2, a lot of water ended up dissolving in the atmosphere, in the magma?
You mean this calculation?
Mhm.
So um, is it because of solubility? Is actually not. So I didn't talk about this, but the dashed lines, the dashed curves, are the curves where we ignore the solubility laws.
hmm
And they have an effect, as you can see, I mean, this is many orders of magnitude, so it has the effect of factor of several, at least, on
hmm
the computer abundances. But you see, the effect is not large enough to say hydrogen or not.
So the hydrogen here is primordial, is it?
Yes, it is.
Okay.
Yes, it is.
So this is the polluted atmosphere, and at high temperatures, you're not outgassing enough because the pressure's too high to allow outgassing. Is that the way to think of it? Whereas
It's,
at low temperatures, at lower masses, outgassing is more efficient, and you get more water coming out.
there are a few things to say. You can outgas hydrogen, but this is not what you're seeing here. So here, the calculation assumes that you have 10,000 bars of hydrogen. And what this calculation is then doing is that it's calculating essentially the thermodynamic partitioning between different molecules.
hmm
And I don't have a very intuitive explanation for you about for why the Gibbs free energies behave in this way. But if you put in the Gibbs free energies, then it predicts that as you go to lower temperatures, the partitioning would favor the increase of these other molecules at the expense of hydrogen. And you
hmm
do this in a way that conserves mass. So the mass of the system is constant. I'm just rearranging how hydrogen, carbon, oxygen, and so on are divided up among the molecules.
I think I get it. So more under those conditions, more oxygen comes out, and you get more water. hmm And now I guess let me follow up then. So if would there be an impact depending on what the core was made of? I mean, I guess the core is always going to have, iron and but if the core was very volatile poor, but I guess this would still have silicates and so would still have oxygen, would you be able to tell the difference between that and a core that was initially very water rich?
It as the core absolutely plays a central role in this, and in particular, how much oxygen this core has, which is very difficult to calculate, would absolutely affect what's going on. So
hmm
this is expressed as the oxygen fugacity. I think that's a subtlety here that I'm still thinking about. I've had various discussions with people, which is that there's a subtle difference between the bulk abundance of oxygen of the entire planet and the amount of oxygen just in the thin layer where the mantle resides.
hmm
So if you look at the Earth, for example, the bulk oxygen abundance of the Earth and the oxygen fugacity of the Earth's mantle are quite different. And
hmm
it's actually the oxygen fugacity at the mantle that controls the outgassing.
hmm Well, let me then ask a final follow-up, and then we can hopefully others will join in here. But let's say I had my core, and then I had a primordial atmosphere with some chemical composition that may be reflected, that I'm interested in. In the early phase of the planet, a lot of the metals might dissolve from the atmosphere into the magma, as maybe what I learned, but then they would outgas back.
Yes.
So would after that process, would I just have back what I had in my initial primordial atmosphere? Would I be dominated in that regime? So I would what I measure billions of years later would still remember that? Or is it more likely to just be completely changed by what could escape out of the core, I suppose, is the question.
Is it, yes, so what you in-gas will eventually outgas, but not in a straightforward way. It again depends on the thermodynamics of the outgassing, which is what this plot is trying to show. Meaning that just because you in-gas some amount of water does not mean that you will get out the same amount of water
Hmm.
because the oxygen and the hydrogen in the water may be partitioned differently among different molecules. So you could in-gas water originally, but you could outgas a combination of other things
Hmm.
in a way that perfectly conserves the mass of the system if you forget about atmospheric escape in this discussion. Um, so in other words, the lesson is that um, if you would really like to understand in detail the atmospheric chemistry of the envelope, you couldn't just do simple chemical systems with just hydrogen, water, and metal. You would have to include carbon, you would have to include sulfur
Hmm. Hmm.
and silicon and so on.
Great. There's a question in Virginia, so please.
Yeah. Yeah. Hi, Kevin.
Hi.
I was wondering, like, what caused outgassing of nitrogen in Earth's, because I didn't see nitrogen again in your models, right?
Well, nitrogen is actually the origin of nitrogen on Earth and how much it has and how much it interacts geologically is something that's still being debated. And it is actually part of the motivation I didn't include it because my motivation was to understand the mean molecular weight of the atmosphere. So including carbon, sulfur, oxygen, and silicate was already sufficient in that sense.
Okay. I have another stupid question. So, so I didn't understand what causes radius valley then, because from what I understood is that your models are like smooth gradients of mean molecular rate and outgassing. So, what caused this like bimodal distribution? I didn't
This
follow the logic.
this comes from this paper. It's not my calculation. So this paper, um, basically, what they do is they assume a single underlying exoplanet population. They they define. You have to read the details in the paper. They define in various ways some distribution of core masses, atmospheric mass fractions, and core densities. Then for every draw in this distribution, they try to match the radius valley. And they do that by matching both radius and orbital period and evolving the planets through 3 gigayears of photoevaporation. So they do this in a using an MCMC. So they keep repeating this draw till they end up with a model distribution that matches the observations.
Hmm. But let me follow up then. But in this model, let's say where you just evolve your atmospheres by evaporation, but you have no outgassing from the core, you'd still have an increase in mean molecular weight across the radius valley, I think, wouldn't you? Because you mainly lose the hydrogen and helium.
In this model, not in reality. Reality is always more complicated. In this particular model, I try to defend this as best as I can, but this is not my paper,
Yeah,
right?
I
So in
know. I
this,
know they didn't account for the chemistry in the atmosphere
right.
or and so on. But in reality, if we observe the mean molecular weight increasing across the radius valley, that could still be consistent with just evaporation from a primordial atmosphere and no outgassing, or would it require outgassing, I guess is the question.
Um, so one way of answering your question is that the calculation is not self-consistent in the sense that this paper has assumed that that atmospheres are mostly hydrogen dominated.
Hmm.
But of course, a better calculation to do is to account for the fact that you have outgassing in the manner I described to you. You would then repeat this calculation with the outgassing and the escape simultaneously
Hmm.
and try to match the observed population. And then you have very interesting effects, like the fact that as your atmosphere becomes heavier, so to speak, as it becomes as the mean molecular weight increases, it actually protects itself from evaporation because the scale height decreases, the atmosphere gets heavier, and it's actually harder to lose it, all things being
Right.
equal.
So you change the shape of the radius valley compared to their simple model.
Exactly. So if you redo this calculation with a self-consistent treatment of outgassing and escape, you would end up with a distribution of core masses and mass fractions that will be different from what
Mhm.
they show here.
Well, maybe that's a calculation we'd like to do then. I think you mentioned before you have a code that you've released that does some of this physics. Is that right?
Rogers and Owen has they have a code that does this basic calculation,
Mhm.
and I have outguessing code and that I develop. And in this initial study, we have combined them in a way that's not self-consistent.
Ah, mhm.
But again, what is interesting in this study is not the fact that you are just smacking two codes together. What is interesting in this study is that the temperature pressure conditions that are needed for the outgassing are informed by the Rogers and Owen study.
Mhm.
So I'm not blindly guessing what the T and the P's are. I'm taking it from the evolution model of Rogers and Owen, and I'm using that to inform my outguessing. And the reason why that's critical is because as I showed you, the outgassing chemistry changes quite dramatically over a rather short range in temperature. So the calculation will be meaningless if you Monte Carlo over the temperature. You will not get the physics right.
Mhm. Very good. And I know we're running up against the clock here, so let me just, are there any last questions from anyone online or in the rooms in Sweden and Virginia?
Can I show you this last slide that I didn't talk about? That actually I found the most exciting.
Yeah,
Uh,
please.
I don't have time to explain it, but uh, here's a different way of showing this calculation. So again, this calculation is when I take every sub-Neptune generated by Rogers and Owen, and I take the TP conditions in these calculations, and I generate outgassing model for every point you see, and I calculate the mean molecular weight. So this is another way of presenting the same set of calculations, which is that I present the mean molecular weight first against the oxygen fugacity, so how oxidized the cores are, and then against the carbon enrichment of the atmosphere, which is the so-called metallicity. And what is really striking is that you see as you go from low to high oxygen fugacities, the mean molecular weight increases in the ensemble sense, but the metallicity or the carbon to hydrogen ratio doesn't have the same effect.
Hmm.
So to lowest order, at least in this toy model, it suggests that it is the oxygen fugacity that controls the mean molecular weight, not the metallicity that a lot of people are thinking about.
Hmm.
And if you talk to geoscientists, they would say, of course, this is exactly what I would expect. Whereas in astrophysics, we are so used to thinking about metallicity that we keep thinking about metallicity, but actually it's the oxygen fugacity that's the important parameter here.
But now remind me, is this fugacity measured? And so it should not be varying over such a wide range, or is it so uncertain, or is it varying because of conditions? You have to remind me.
This is the weak point of the study, which is that I have no theory to predict what the oxygen fugacity should be for a given Neptune, because it is more than just saying for this given rocky core, let's assume some bulk oxygen abundance. It's much more than that because you have to produce a core that is geochemically plausible. So given the iron and the silicon and the magnesium and so on, you have to differentiate the core. You have to figure out how much oxygen is in the core, how the oxygen changes as you go from the center of the core to the edge of the core, which I have no theory for.
Mm.
So in this study, which is why I call it a toy model, I have just assumed a very wide range of oxygen fugacities, and I have randomly sampled the oxygen fugacities in a log sense. And given the lack of theory, this is the best I can do.
Mm.
But it's quite striking that even with such a naive sampling, you get this effect.
Mhm.
And now if you put in some relationship for the oxygen fugacity, say you don't like what I've done, and you said, I believe that due to atmospheric escape, that smaller objects should have more oxidized mantles, say. I do not know. There's a 2025 study that suggests this, then it actually strengthens our conclusion because if you now give it an oxygen fugacity gradient in the same direction, this actually enhances the effect I just described to you. This would drive the mean molecular weight gradient even higher as you go towards the valley. So
Mhm.
all things being equal, the prediction is that if you go out and you measure a sample of sub-Neptunes and you measure their atmospheric chemistries and you convert it into mean molecular weights, you should see that as you approach the valley, these things should have strongly non-hydrogen dominated atmospheres.
Mhm. Mhm.
What that tells you about the oxygen fugacity of the core and the formation conditions, I have not thought very carefully about.
Mm. Well, but you have a new geo astronomy center to, or many years to work this out. So very good. Well, I think we should wrap up the time now. So let me stop the recording and let's thank Kevin again.
Thank you for your patience.